This work focuses on understanding the complex potential energy landscapes that govern the structure and dynamics of classical mechanical systems, particularly in polymer science and condensed matter. The central question is how to characterize transitions between stable states in these systems, which correspond to minima on the potential energy surface or free energy landscape. This matters because such transitions underlie critical phenomena, such as molecular conformational changes and chemical reactions. The authors approach this by picturing potential energy as a high-dimensional landscape where the energy value corresponds to topographic elevation and the system's configuration defines the coordinates. At low temperatures, transitions occur via saddle points on this landscape, analogous to mountain passes connecting valleys. The paper describes computational and theoretical methods to identify the states, pathways, barriers, and rates of transitions on these landscapes. This includes methods to approximate reaction pathways, calculate free energy barriers, and estimate reaction rates, providing insights into molecular dynamics from a mechanistic and statistical perspective. The general strategy combines conceptual landscape models, numerical simulations, and statistical mechanics to elucidate system dynamics. Figure 1 offers a visual analogy depicting a complex potential energy surface, or PES, as a landscape with multiple minima, maxima, and saddle points. The system's configuration space is represented in the XY plane, while the vertical axis represents the potential energy at each configuration. This low-dimensional depiction is a simplification, considering the true high-dimensional configuration space of a system of many atoms. The energy landscape contains numerous valleys representing stable states, peaks as energy maxima, and saddle points corresponding to transition states. At low temperatures, transitions between energy minima typically occur via these saddle points, which act like mountain passes connecting valleys. The example shown arises from the Gaussian core model, where a single particle moves in a fluid of many others, interacting via a Gaussian pair potential. The potential energy landscape was computed by moving one particle in the plane, while fixing others to a typical fluid configuration. This visualization helps conceptualize how the system can transition between different configurations, overcoming energy barriers that separate these stable states. The authors interpret this representation as a useful but necessarily simplified metaphor for the actual complexity of these high-dimensional energy landscapes. Figure 2 illustrates an approach to determine transition states and minimum energy pathways between two adjacent potential energy minima through a chain of states, denoted R0, R1, as Rm. Each state represents a full configuration of the system. Analogous to an elastic band, the chain spans between the two minima fixed at its ends. The method aims to relax the chain states to minimize an objective function depending on both the springs, connecting adjacent states, and the underlying potential energy surface. The nudged elastic band, NEB method, is one prominent example, where spring forces act tangentially along the chain as described by the tangent vector, and potential forces act perpendicular to ensure the path approaches the minimum energy route. This relaxation procedure results in a minimum energy path that passes through the saddle point between minima, effectively mapping the most probable transition route. Importantly, while the chain represents a discrete sequence of system configurations, the forces acting are constructed to ensure smoothness and physical relevance of the path, even though the objective function need not be directly related to the system's true dynamics. This chain of states approach is critical for exploring complex energy landscapes where transition details are otherwise difficult to resolve. Figure 3 shows a free energy profile FQ plotted as a function of a reaction coordinate Q, illustrating a bistable system with two stable conformational states A and B. These states correspond to free energy minima separated by a barrier of height delta F, located at Q star, representing the transition state. This type of free energy profile is typical for processes such as molecular isomerization, where a molecule switches between two different conformations. The figure also depicts a trajectory as a thin, wiggly line, illustrating how the system fluctuates predominantly near the stable states, but occasionally crosses the barrier from one state to the other. This barrier controls the kinetics of transitions, as it represents an energetic threshold that must be crossed. The reaction coordinate Q is a reduced variable capturing the essential progress of the transition, making visualization and theoretical treatment feasible. Understanding this energy landscape helps explain why the system spends most time near the minima and why barrier crossing events, although rare, are crucial for the system's dynamics and function. Figure 4 illustrates the dynamics of the reaction coordinate Q of T over time for the bistable system with free energy shown in Figure 3. The top panel displays Q of T, showing that the system typically fluctuates around the values QA and QB associated with the stable states A and B respectively. Transitions between these states occur infrequently and appear as swift switches compared to the relatively long dwell times near each minimum. This separation of timescales is a hallmark of activated processes where the system spends most of its time trapped in stable conformations and rarely crosses the energy barrier. The bottom panel shows the indicator function HB of T, which equals 1 if the system is in state B and 0 otherwise. This step-like function simplifies the dynamics by focusing on whether the system resides in region B at each time point, providing a coarse-grained temporal description of state occupancy. Following this perspective facilitates studying the statistics of transitions themselves, neglecting rapid microscopic fluctuations within stable states. The authors interpret this as a useful reduction for understanding activated transitions in complex molecular systems. Figure 5 presents the typical behavior of the reactive flux function K of T used to estimate reaction rate constants. Initially, at time 0, the rate K0 corresponds to the transition state theory TST approximation, which counts all crossings of the dividing surface without considering recrossings. Immediately after t equals 0, correlated recrossings lead to a decrease in K of T, reflecting that some trajectories cross back and forth, reducing the effective rate. After a transient period shorter than the molecular timescale, tau mole, K of T settles on a plateau whose value equals the true forward reaction rate constant, KAB. This behavior highlights the central insight of TST, that the reaction rate can be approximated by the flux of trajectories crossing the dividing surface at the transition state. Practically, one first computes the free energy FQ to find the transition state position Q star, then determines the average positive flux of trajectories through this state. For example, via constrained molecular dynamics, the product of exponential barrier crossing probability and average positive velocity yields the TST rate. However, as the figure indicates and the authors note, TST typically overestimates the reaction rate since it neglects recrossings that reduce the net flux. Correcting for these recrossings refines rate estimates and provides deeper kinetic insight. Figure 6 depicts a two-dimensional potential energy surface with contour lines of equal potential energy. The stable states A and B correspond to minima on this surface, while the transition state TS is a saddle point that must be crossed during a transition between these states. The saddle point is characterized by one unstable mode, indicated by a thick arrow pointing along the direction in which the energy decreases towards both states. The dividing surface used to separate reactants and products is a plane orthogonal to this unstable mode, shown as a dashed line. A reactive trajectory, plotted in red, crosses the dividing surface twice, showing that recrossings can occur where the system transitions back and forth. The authors discuss that at low temperatures, the potential energy near the minima and saddle point can be approximated harmonically by a Taylor expansion, enabling analytical calculations. Normal mode analysis of the Hessian matrix identifies the unstable mode with a negative eigenvalue at the transition state, which defines the reaction coordinate direction. This geometrical picture and harmonic approximation simplify the theoretical framework for transition state theory and reaction rate estimation. However, the presence of recrossings, shown by the trajectory, indicates that corrections to simple TST may be necessary for accurate kinetics. Figure 7 provides a schematic view of the fundamental setup for the transition path sampling, TPS method. The stable regions A and B correspond to distinct subsets of the system's configuration or phase space, characterized by microscopic variables that define these states. Each region is stable in the sense that if the system starts within it, it remains confined there for a long time due to energetic or entropic barriers. Transition paths of interest are those trajectories that start in stable region A and end in stable region B. Only these paths have non-zero weight in the transition path ensemble, TPE. This ensemble excludes all trajectories that do not directly connect A to B, focusing analysis on the mechanism and statistics of rare but important transition events. The TPS method samples these reactive trajectories to characterize transition mechanisms without prior knowledge of the reaction coordinate or barrier location. This conceptual framework allows for understanding dynamical pathways in complex molecular systems, isolating how transitions proceed across high-dimensional landscapes. Figure 9 illustrates the transition interface sampling TIS method designed to efficiently calculate reaction kinetics by defining a series of non-intersecting interfaces between stable regions A and B. These interfaces correspond to increasing values of a suitable order parameter. The effective positive flux of reactive trajectories crossing these interfaces is measured via separate path sampling simulations for each adjacent interface pair. In the path ensemble corresponding to interfaces I and I+1, only pathways that start in A cross interface I and then either cross interface I+1 or return to A are included. This is visually depicted with red paths representing allowed trajectories and blue paths excluded because they do not cross interface I. Such decomposition enables factorization of the overall rate calculation into manageable conditional probabilities. The sampling involves generating new trajectories by randomly selecting slices on existing paths and evolving them using shooting algorithms, accepting those that meet TIS ensemble criteria. This method enhances sampling efficiency compared to fixed-length path methods, facilitating rate calculations in complex systems with high-dimensional order parameters. The approach has also inspired related methods like forward flux sampling for stochastic non-equilibrium systems. Figure 10 explains the concept of the committer probability PBR, which measures the likelihood that a trajectory initiated from a specific configuration R will reach stable region B before returning to A. To compute PBR numerically, many trajectories are started from R with randomized initial momenta sampled from the Maxwell-Boltzmann distribution. The fraction of these trajectories that first relax into B rather than A gives the committer value. This probability serves as a precise quantitative measure of how configurations relate to the transition mechanism. It refines the quality of a chosen reaction coordinate by revealing how well it stratifies configurations according to transition likelihood. The committer was first introduced by Onsager as a splitting probability and has since proved invaluable for analyzing complex biomolecular processes such as protein folding and nucleation. By bridging microscopic configurations and transition probabilities, the committer enhances our understanding of reaction pathways in high-dimensional space. In summary, this paper explores the theoretical and computational framework for understanding transitions between stable states in complex molecular systems governed by potential energy surfaces and free energy landscapes. Through an illustrative series of figures, it presents methods to identify and characterize stable minima, saddle points, and transition states on these high-dimensional landscapes. By mapping transitions onto chains of states and employing methods such as the nudged elastic band, transition state theory, and transition path sampling, the authors describe how to compute reaction pathways, barrier heights, and reaction rate constants. The use of order parameters and interfaces enables efficient sampling of rare transition events, while committer probability quantifies the quality of reaction coordinates and provides detailed mechanistic insight. These concepts unify landscape metaphors with rigorous statistical mechanics and molecular dynamic simulations, offering powerful tools for studying activated processes across physics, chemistry, and polymer science. The approach balances computational practicality with physical accuracy, addressing challenges like recrossings and high dimensionality to advance our understanding of molecular reaction dynamics.